Today we're going to talk about using structured data in RAG. We're going to actually really go through RAG, not just from like how do we use structured data in RAG, but I'm actually going to kind of go pretty broad around LLMs building those sorts of pipelines. So this is a good one. Obviously, we're going to get into some more advanced topics, but I would say it's a really good kind of beginner intermediate one. Um, Without further ado, I'll share my screen and get started. Okay. Um, I want to talk about the kind of components of an LLM pipeline, of when you have an LLM product in production. There are really four um, pieces. Now, I actually want to draw an analogy to traditional machine learning. Assuming some of the people here maybe came from a more traditional ML path and have moved to LLMs, I think this analogy can be really valuable. In ML, in like traditional machine learning, we have a data step, and we have a training step or experimentation step. We have a deployment step, and then a monitoring step. So interestingly, in an LLM, in production, like the pipeline looks very, very similar. Like first, there's still that data step, which is where you build all of your features and prompts and everything that kind of goes into the model. We'll talk obviously more about using structured data there. Um, Training becomes optional, but it is very akin to fine tuning, where you're literally giving it like a here's an input, here's an expected output, and you're training. Deployment is either similar or an API. If you're just using GPT, you might just be hitting an API call. If you are building from scratch, or putting Llama or something into your stack, then you are deploying as you would deploy a typical deep learning model, perhaps a bit bigger, but same sort of idea. And then monitoring and evaluation is the same. Um, it's obviously like a bit of a different context, but monitoring and evaluation, interestingly, is very similar. Well, what's another component to notice is that in practice, the hardest pieces of traditional machine learning were typically the data and the monitoring and evaluation. And in LLMs, it's kind of become the case as well. The hardest pieces are again the data and the evaluation. Cool. So I've thrown around RAG. I've thrown around uh, I've thrown around RAG. I've thrown around fine tuning. What do these things mean? So first, let's just build up from scratch. We've all used ChatGPT, I'll just assume. And so we've all gone through this exercise where we, as a user, write a query, or just we have a thing that we want to learn. Like, hey, I give me a recipe for chocolate chip cookies, and that's my intent. And then I'll turn that into a prompt. I'll feed that to LLM, and it will give me a response. This is a base LLM operation. You can do this programmatically, like from your own application. If you're building an app, you can uh, build an app that takes something that the user does, turns it into a prompt, does an API call to OpenAI, and returns a response. The nice thing about this architecture is it's super easy. It's an API call, one, and then two, it kind of feels like magic. Like it's sort of unbelievable how good it is just from base. The cons is one, it hallucinates. It tends to just like come up with things. Two is stale data. A lot of it depends on the type of model you're using or which model you're using, but with a lot of models, they they're trained at a specific point in time, so they won't have relevant new context. Um, Three is undifferentiated responses, which is you can't if you are trying to compete. This is more relevant if you're kind of like building a startup or building a product to compete with another product, you have no differentiation. I mean, it's just an API call. And then, so it's very easy to copy and mimic. And then finally, and probably the most important piece of us of why we don't just do base LLMs in production grade pipelines is there's no context. It doesn't because it doesn't have context. If I were to ask, how should I invest my money to a bank LLM, and Marie was to ask, we would get exactly the same response because it would be the exact same API call. It would actually be a slightly different response, but they would be more or less the same response. Um, but it wouldn't have all the context it would need. And in practice, like the answer to that question might be different for us too. And so having that context is extremely important. It doesn't even really have context of like it's a chatbot for a specific bank. So it's missing, it just doesn't have anything. It just you're just giving it some text and having it respond generically. So one approach to solve this is to build a fine-tuning loop. So what fine-tuning is before you start using a model, you give it a handful of examples. Like here are some potential prompts, and here are some responses. So we have a kind of silly example here where I'm fine tuning it, I'm having it respond or showing it what I would like it to respond to specific questions. In doing so, um, I can then put that back into the same base kind of API, and it will do better. It will be contextualized. It will just be different from a stand or the base model. The pros of fine tuning is one, the training step looks really similar to like machine learning training steps. So we have architecture around this. If you're using some labeling company, like you can very much use the same labeling company to do it, to take advantage of it. Two is if you have like existing chatbot and you have large data sets, you can take advantage of those to accomplish what you want. And then three, again, you can use that reinforcement learning from human feedback, RLHF. What that really means is, in a very simple example, you could just hire someone and have them go through 1,000 prompts that users have given and just write out manually what a perfect response would be, and then train on that. So it becomes really easy to you can train, and you can train in a way that we in ML we're very used to. The cons, it still hallucinates. It will always hallucinate. That's kind of just part of how LLMs work. Two is it's bad at memorization. Um, when doing fine tuning, you aren't in practice doesn't always really memorize well. So if you give it one data point about one person, it won't really remember that. Three is you kind of want either a really like good amount of data or a lot of data or like a really specifically like cold perfect data set to really see strong results. Four is two-part, which is subject to prompt injection. Because as you notice, every single person is using that same fine-tuned LLM. So every user of your application uses the same thing. That means every user of your application um, asking the same question will get the same response. So, for example, I might say, "Oh, my name is Simba, and this is my question." It might have examples of how in the training data of how it should respond to that, and so it will give me a response that's fine-tuned to me. But I can also just write, "Hey, my name is Marie, and here's my question," and then I can actually get it to respond and perhaps spit out data that is personal to someone else. So the problem with fine tuning is that all of the information that you feed into the LLM is in the LLM for given the right prompt and assuming the LLM actually memorized it, you might be able to get to spit out some really specific user data. So in practice, you should use fine tuning more as a stylistic thing. It's like a here's how I want you to respond to questions. It's not really meant for here's information I want you to learn. So the final thing is RAG, Retrieval-Augmented Generation. Uh, RAG is it's kind of I would say the most successful architecture that we've seen around um, LLMs. RAG stands for, again, Retrieval Augmented Generation. To break that down, retrieval, I'm retrieving data for context. Augmentation, so I'm augmenting my prompt with that data. And then generation, which is just what an LLM does. So it really just means get data, put it in my prompt, generate a better response. So that's RAG. So for example, if a user asks, how should I be investing? You can retrieve features such as their age, how much money they have, average spending per month, spend category. You can retrieve maybe you have wealth advisors and there's all their conversations are recorded. And maybe you've picked out some like really good responses to questions. And so you can pull those in. In fact, if the user specifically has a wealth advisor they've talked to, you can even pull in information from those conversations. So then you will have kind of this like set of data of relevant context, relevant to their intent. And you then feed it into the model via prompt structure, because in the end, the model still only takes prompt or a text input and then text output. So you can say stuff like, hey, given the user has these attributes and using context from a blog as context, how should I or answer this question? And then you typically feed in the original question into that prompt structure. So you're kind of taking their question and enriching it with context and data. The benefits here is that this is actually one of the few places where you can really drive down hallucination because you are feeding in specific data. For example, one thing that we've run into here at Featureform is uh, if you ask ChatGPT about how to use us in specific ways, it will sometimes make up API calls that don't exist, like we don't have. And so to solve that, you have to pull in actual data from our docs and tell it, hey, this is all the relevant things we found in the docs. We might not be able to do this. And like you have to structure your prompts so that it doesn't make something up if it doesn't know. Safer from prompt injection, because the private data is in the request. It's context bound, which means that if I do a request and then Marie does a request, like the context will only be in each of our individual requests. It won't be in the model itself. So there's no way for her to see my data and for me to see her data. It works really well and it's really durable, which means that similar fine tuning, you can kind of really you can iterate on this. You can play around with things. You can try different data sources. You can try different types of context to see what happens. The cons is it tends to be pretty complex, one, and then two, it requires a large enough corpus of context to be useful, which means if you have a million users and they're asking all sorts of questions, you want to make sure that you have enough coverage of like context across all those users for it to not just generally do nothing and just do the base thing. Cool. So you'll notice that RAG is more or less focusing on the data and fine tuning is focusing on the model. So in the four stages that we opened up with, uh, data and training are kind of the two steps. I also want to add that I think a lot of people think of it as a dichotomy, like you need to like which one are you doing, fine tuning or RAG? I actually think it's totally fair. I mean, you can do both. There's actually no real drawback of doing both if you would get benefits from it. So yeah, I mean, don't treat it like you have to pick one. You can do both. It's just more which one's going to drive more value if you only have the resources for one or the data for one, etc. Okay, so let's talk about RAG a bit more. Let's break it down some more. So a really common thing to do is, for example, take your, let's say you have your customer service reps, you're building a customer service chatbot powered by an LLM. So you can take all of the conversations that have ever happened with your customer service reps. Um, you can chunk them into right-sized pieces and then store them in some sort of search engine, some way to um, look them up. And typically that's done via vector database, via embeddings, which I'll talk about in a moment. I want to talk about chunking. So let's say that each customer service conversation is super long. It's like, you know, 100 paragraphs. I don't know. That would be more relevant in like maybe uh, a PDF context of like you, let's say you are a LLM oriented towards JavaScript frameworks. And so you pull all of the docs of every single JavaScript framework in. If someone asks about, um, I don't know, if they ask about Flask, and then you take the entirety of, or it's a very specific question about Flask, and then you do a search lookup, and then you pull a chunk, and that chunk is as big as the entire Flask docs, and you feed that into the LLM, it may do okay, but in practice, most LLMs kind of tend to, especially LLMs actually with larger context windows, they tend to fixate on the closer context. So if you give it too big a context window, it will miss things. So if there's like a few sentences hidden amongst this like, you know, book and you ask it a question, it's actually unlikely to find it. Depends on the model, depends on the question, depends. It's very specific, but in practice, if you can, um, you know, confidently prune off pieces of the context that you know are not relevant, then it's going to probably do better. So that's where chunking comes in. Chunking allows you to kind of grab, because you're going to grab n paragraphs that are similar to the intent. So having the right size pieces allows you to grab the right ones. If they're too big, again, it's just too much. You might even overrun the context window, in which case you can't even use all of it. The problem of going too small is you might end up with like some haphazard random sentences from their docs and just try to stitch them together, which might actually be more confusing to the LLM than it is valuable. So getting the right size chunk is a bit of an art and something to play around with. So once we have all those chunks, we typically create embeddings from them. An embedding is literally just a vector. It's like n floats, and it's a vector that you can specifically. It's spatial, so you can specifically put it in an n-dimensional space. That's a little hard to visualize. So usually when we're visualizing it, um, we will map it down into like a 3D space or a 2D space. So here we have like a 3D space in this image. What embeddings do, they have the quality that things that are close to each other are considered similar. Um, so by similar, I mean they are, yeah, it just the model decides that these things are related to each other in some way. Embeddings are really good at figuring out things that are a bit hard to like explain. For example, in this example that you see on screen, just from the images, it was able to put together like on the bottom left, you can see it put together pants and leggings. So it's separated out pants and leggings, but they're kind of closer together than they are to shorts, which are on the other side, which makes sense. To a person, like that's totally obvious why leggings and pants are closer together than shorts. Um, but it would be kind of a weird or hard thing to uh, manually codify all these relationships. And so what embeddings do is they codify it automatically. Now, we tend to do it with text for RAG. And so you will take paragraphs or chunks and you will put them so that chunks are related. So if we're doing like docs for a product, all the docs talking about similar concepts will kind of be closer together than docs about other concepts. And they'll also cluster in that, like maybe you have some parts of your docs are about deployment and some parts of your docs are about the API. So the API doc should cluster, and then the deployment docs should also cluster. So that's kind of how embeddings work. Um, we use them in two ways. The way that's relevant in RAG is that we can embed like a text, like for example, a user's question, and then use that to do a lookup of n things from the vector database, which is the context that we feed into the prompt. In traditional machine learning, we'd also use them in different ways. Like we could feed them directly into models to accomplish things. Because you can use them as features. Um, So I talk about retrieval. This is where vector databases come in. Vector databases are just specialized databases that they obviously store embeddings, but that's actually not the hard part. It's very easy to store embeddings. They're just a flow of vectors. The hard part is how do I efficiently do a nearest neighbor lookup? Um, Nearest neighbor lookups done correctly is a very computationally expensive problem. So vector databases all use approximate nearest neighbor lookups. So they have an index and they have a specialized index to do approximate lookup. Great. So that's the context of the content and RAG. People typically, when they say RAG, they mean, yeah, I'm embedding my text and then I'm doing a embedding lookup. Now, the thing is that the actual problem that RAG is solving is not just, it actually has nothing to do with embeddings at all. Obviously, embeddings are a tool to accomplish the problem, but it's a solution. It's not actually like the this is how you do RAG. The problem is that I have a context window. That context window is a fixed size per model. If I overrun it, then I obviously can't use it. So I need to fit as much relevant information as I can in this context window. If the context window is huge, then I also probably have the other uh, problem where the if the context is bigger, the chances of the model efficiently using it all drops. So it's still valuable to like really grab the most relevant chunk of context. Um, if I'm asking questions against like a PDF or like for example, I'm asking questions about Featureform's API, um, it can be totally fair that uh it could be totally fair that I just do content embeddings and just do the thing we just talked about. But it's not actually the best tool for all problems. For example, I mentioned the bank example, and some of the features there, like age, money in bank, average spending per month, spend categories, like it's kind of clear that those things would be valuable for as context. But those things don't exist in a vector database. It would be kind of a strange thing to fit that into a vector database. Um, it would typically exist in like a Postgres database or something, a more traditional database. And you would retrieve them via just a normal key value lookup. And then there's another common problem, which is relevant to the analytical features, which is graphical features. Now, imagine, like, think of Copilot, GitHub Copilot. When you're looking at a function and you're writing code and it's generating code, it's not doing like RAG. It's it's actually looking at what you're looking at, and then it's built a like graph or like a yeah, like a dependency tree of all the like functions being used, all the functions that depend on this function, and it's building the context of what is this function in the context of the code base. And that's what it uses to generate. But actually, in that situation, the context window is full of data, but that data actually um, has nothing to do with like embeddings and lookups. They might do some, but doing like a embedding lookup on like a Python function is not really that useful typically. Depends on what you're trying to do, but it's not gonna usually be as useful as actually just looking at and fitting in like all like, hey, this function calls these three functions, and here is the code of those three functions, and like kind of doing that sort of thing will give you way more valuable context than here are functions in my code base that kind of look like this function. Um, so breaking down this like complicated image, um, there's really two parts. There's the per request piece. So user makes a query, you pre-process it in some way, perhaps. Sometimes people don't. Sometimes what people do is they'll take the query, they will ask ChatGPT for a generic answer, and then they'll use that generic answer actually to do a lookup. So there's all kinds of tricks you can do on the query to get a better embedding so that you can get more relevant context. But anyway, like the simplest case and the more common case is just use the query, create an embedding of the query, and then hit a vector database with that query, and that will give you back relevant chunks of text. At the same time, you also have like the user ID and any other IDs like the function ID and other context. And you can do that off of your graph databases or your inference store to retrieve other relevant context. So now you have all these like kind of bits of strings, really, just bits of text that you then fit together into a prompt, and then you ask LLM and it gives a response. So that's RAG per each request. So every time you're using an application doing RAG, every request looks like this. On the other side of it, though, like you have to actually fill those databases with data. And so you'll typically have an asynchronous step that every time a document gets processed or gets uploaded, you pre-process it, you chunk it, you do what you need to do, you embed it, and you put it in the vector database. Same with tabular data, you might have like some streaming transformations, taking streams of user events and other things and putting them into features that go into the feature store. So all this kind of fits together to be RAG. So you have one piece, which is building your context. Yeah, really just building your context cache. And then another piece, which is per request, grabbing proper context from that cache to feed into the prompt. Um, cool. I'll pause. Is there any questions so far? I'm gonna kind of jump around a bit, but uh, yeah, any questions so far? I actually missed a slide on embeddings I'll talk about real quick. Um, but if you have questions, if you're on LinkedIn, feel free to throw them in the comments. And then if you're in the Zoom, you can throw them in chat. If you're on Twitter, you can also leave them in the comments. So this slide didn't get moved. This is how we create embeddings. We actually use models to do it. Those models are called transformers. Um, we they're not the guy in the middle. They're look closer like the thing on the left. Specifically, they are encoder transformers. One of the most famous ones was one called BERT. It's not really the standard anymore. It's a bit old now and a bit dated. But most of what we've seen in the boom of ChatGPT, you can almost directly link back to a paper that introduced a model called BERT. Okay. So RAG can be kind of complicated. You know, there's a lot of pieces here. There's a lot of pipelines to set up and orchestration you have to make all this work. Um, that's why we at Featureform believe that a data orchestrator needs to exist for all this. And that's what Featureform is in the LLM context, is your data scientists can still write their own Python code to transform. They can work in notebooks. They can come up with the right context cast, the right types of lookups they want to do, and feed that to Featureform. Featureform will then continuously update your cache based on new data coming in, and will also give you some like kind of functions you can call that will generically do near stable lookups and other things that you need. This all sits on top of Spark, Redis, V8, whatever else you use. So one, you're using best in class infrastructure underneath the hood. And two is it can scale to really massive scale, like petabyte scale. Um, so that's Featureform. It's open source. You should definitely check it out. You probably run into the problem if you've built RAG pipelines, or if you haven't, you will, where it just things can get super out of hand. Like it can get really messy. Like how did we chunk this? What's in this table? How are we using that table? Which models and LLMs are we using that actually use those features? Like you might be changing things or trying different chunk sizes and just keeping track of what uses which things can be really complicated because typically it's not really documented very well and the code can get kind of ad hoc. So that's why Featureform exists. Um, I want to finish off by talking about fine tuning, just because I think it's kind of the other component of RAG of LLM applications, which the stage of fine tuning is that you will have a set of user answer pairs or rather question answer pairs. So you might do these manually, or you might just take data that's existed before. Most models have some sort of API to do fine tuning. And it will typically output some sort of model. It could just be a string or something, some model version that you can then store and keep track of. So that's fine tuning. So fine tuning works hand in hand with RAG. It can work hand in hand in RAG. You can just do fine tuning. You can just do RAG. You can do neither, as we talked about before. Deployment, the third stage. You can use APIs like ChatGPT, in which case deployment is done for you. You can also use vendors like Base 10 if you have open source models, and then you can roll your own open source frameworks like Seldon or Bento, where you're actually taking a model from scratch and deploying it as you would a traditional model. And then finally, there's monitoring and evaluation, which I would argue is the key to production LLMs. Like this is what makes the feedback loop work. This is what makes production systems get better. So you need to track conversations. You need to build systems that catch bad behavior and get user feedback. And then you need to learn to use that feedback to generate more data and feedback into training so that the system just gets better and better and better. It just improves itself over time. So feedback is really key. RAG can get way more complicated. Like you can do re-ranking steps, you can do model generated features, you can have agentic workloads, which are not really RAG, but and then you can also have multimodal use cases where you're actually feeding in images and audio and other things. So it can get really more complicated. Things like re-ranking, for example, I'll talk about because it's really relevant to RAG, which sometimes what people do is they will grab, 1,000 pieces of relevant context, and then they'll have a secondary model that takes those 1,000 pieces of context and chooses based on some model or some heuristic which pieces of context are the most relevant to the specific question at hand. So it really optimizes the information, the context window. And to finally finish off, I also want to be clear. I know there's kind of, again, if people are coming from an ML background, there might be this feeling of like, this is it, like GPT is going to take over everything. I don't really think that's true. I think I can say with pretty high confidence that I don't think like LLMs will take over everything in the next 5 years unless we have a very dramatic shift in model architecture that makes them significantly faster and significantly more efficient, which I don't really think is possible. Or rather, it's not. It would take a humongous jump in research, but it's not. It would be like a whole new architecture, a whole new type of model. So it'd be like generating like the next version of GPT, which is not like GPT-5. It would be like a whole new architecture that hasn't existed before. So that will probably take a bit. The reason is for some use cases like fraud, um, traditional models actually work a lot better. One, two, they're way more explainable. So if they do something, you can understand what they did and why. And then three is they're cheaper. Um, you know, the LMs are massive models. Every single time you run them, it can be very expensive. And doing things like fraud detection, that speed and cost, it just doesn't really, and also like quality doesn't really make sense for something that's as like quick and transactional as fraud, as opposed to like GitHub Copilot, where anything that really touches like makes people more efficient, so saves people hours, is a really good use case for an LLM because the cost and timing of GPT from a human perspective, it's like a little slow, like it's a few seconds, but it's not extremely slow. Um, and then two is like if you save me an hour of time, it's like so much more worth the cent or I spent or the penny I spent on the actual thing. So there's that piece, and there's kind of this like interesting middle ground where we might see small language models, embeddings, and just like other types of more esoteric um, things that kind of fit transformer architectures outside of LLMs. So this has existed in recommendation systems for a long time. Um, and in recommendation systems, we've used embeddings for a long time. And so it's not a new concept. And then finally, the other reason I believe this is deep learning evolved with as much as it moved things forward. I mean, it's really the basis of GPT. Um, it didn't kill the random forest. Like the random forest and those types of models are still the most common models in production today. So anyway, I will leave at that. Thank you for listening. I hope this was valuable. And yeah, I'm open to questions if you have any questions. And Marie, if maybe you could also do a little talk about what happens next, maybe while people are writing up their questions.
Yeah, sure. And I also want to mention I'm looking at LinkedIn as well if anybody's watching on LinkedIn and has any questions. But thank you guys so much for taking the time to watch this webinar. After this afternoon, I'll send you guys a follow-up email. It'll have a recording of this webinar. We'll also have links to our Slack community, open source, and also if you have any feedback about our webinars, we'd love to hear it. You can reply to that email as well.
Awesome. I'll give it 30 more seconds if someone has a question. Um, but if not, you can always, like already said, like you can always join our Slack community and ask there if you think of it later. If you need to email me for any reason, I'm easy to find. I'm just simba@featureform.com. Great. Well, thank you all so much.